The armature of a brushless DC motor is a permanent magnet driven by a series of stator coils that are switched on and off by transistors at precise angular positions. Hall effect sensors measure the magnetic field of the rotating armature, information used to keep track of its angular position. The stator coil circuit is similar to that of a series wound DC motor. The coil is represented by a resistor inductor in series. The coil current I is proportional to the difference between a supply voltage and the back EMF. To calculate this current as a function of time, use the equation I equals V minus VB over R times 1 minus E to the minus RT over L. The maximum current is approached asymptotically, but in practice it reaches well over 99% of maximum value within 3 time constants L over R. Similarly, the voltage through the inductor VL approaches 0 within the same 3 time constants as the voltage through the resistor approaches the supply voltage. Just like for brushed DC motors, the torque is proportional to the current with a proportionality constant of K sub T. With no external load on the motor, the brushed DC motor will accelerate until a speed at which the back EMF equals the applied voltage, where the back EMF is proportional to the angular velocity omega via the constant K sub E. In practice, the motor will not quite reach this speed due to minor frictional losses in the armature bearings. When the external load is added, the motor slows down per the torque speed curve common to other DC motors. The back EMF reduces correspondingly, and the extra motor current is used to supply the necessary torque to spin the load. The diagram below shows a simplistic design of a 3-phase brushless DC motor. The 3 phases refer to the number of stator pole pairs shown in the outer perimeter of the diagram. Each pole pair is called a phase. The 2 coil windings in the pole pair are energized at the same time and by the same voltage source. The coils take on opposite north-south polarity because they're wound in opposite directions. The phases are labeled A, B, and C, with the coils given the labels A1, A2, B1, B2, C1, and C2. If a phase winding is energized, it is labeled with a red S or a blue N. If it is not energized, no label is shown. The fact that this motor has 3 phases is not the simplistic part. On the contrary, most brushless DC motors have 3 phases. The simplistic part is that the armature is made up of only one magnet. In a real DC motor, having only one magnet for the armature would provide too little torque to be worth building. Most brushless DC motors have between 2 and 8 magnets on the armature. On the other hand, it is much easier to explain how the motor works when there's only one magnet, so I'll pursue this scenario. The armature is shown in the inner circle. The letter N denotes the north pole of the magnet, and the letter S denotes the south pole. In the 3-phase brushless DC motor, we energize only 2 of 3 phases at any one time. The other phase is off. This gives 6 combinations of polarities that the 3 phases can have at any one time, including non-energized ones. We'll walk you through each of the combinations, which we will call states. Each state is powered by a motor commutation, which we'll explain in the next video. We start in state 1 with the motor in magnetic equilibrium per the diagram in the lower left part of the slide. 3 slides from now, we will wind up in the same place, if all goes well, that is. Phase B is powered with positive voltage, polarized north-south, upper right to lower left. Phase C is powered with negative voltage, polarized south-north, upper left to lower right, and phase A is off. The south pole of the armature is attracted to coil B1, the north pole is attracted to coil B2. We flip to state 2 per the diagram in the lower right of the slide. Phase C is still powered with negative voltage, polarized south-north, upper left to lower right. Phase A is now energized with positive voltage, polarized south to north, top to bottom, and phase B is turned off. The south pole of the armature is attracted to coil C1 and the north pole is attracted to coil C2. In the process, the armature rotates 60 degrees clockwise, essentially chasing the pattern of polarity in the stator windings. We move to state 3 per the diagram in the lower left part of the slide. Phase A is still energized with positive voltage, polarized south-north, top to bottom. Phase B is powered with negative voltage, polarized south-north, upper right to lower left, and phase C is turned off. The south pole of the armature is attracted to coil A2, the north pole is attracted to coil A1. In the process, the armature rotates another 60 degrees clockwise. State 4 is shown in the diagram in the lower right part of the slide. Phase B is still energized with negative voltage. Phase C is powered with positive voltage, polarized north-south, upper left to lower right, and phase A is now turned off. The south pole of the armature is attracted to coil B2 and the north pole is attracted to coil B1. Predictably, the armature rotates 60 degrees clockwise. State 5 is shown in the diagram in the lower left part of the slide. Phase C is still energized with positive voltage. Phase A is powered with negative voltage, polarized north-south, top to bottom, and phase B is now turned off. The south pole of the armature is attracted to coil C2, and the north pole is attracted to coil C1. The armature has rotated another 60 degrees clockwise. State 6 is shown in the diagram in the lower right part of the slide. Phase A is still energized with negative voltage. Phase B is powered with positive voltage, polarized north-south, upper right to lower left, and phase C is now turned off. The south pole of the armature is attracted to coil A1, and the north pole is attracted to coil A2. The armature has rotated yet another 60 degrees clockwise. State 1 is again shown on this slide. The armature is back to where it started. Keep in mind that the brushed DC motor is rotating continuously, not stopping at the locations that we defined in these slides. The higher the frequency at which the phases switch polarity, the higher the RPM of the motor. Here is an electrical diagram for the motor driver. The voltage in each phase is controlled by the state of two transistors. The gate drivers are not shown for simplicity's sake. Suffice to say that you can buy gate driver chips these days that control the proper voltage levels for the transistors. Brushless DC motors require more wires than you see on most motors because they must supply high current power to the phases and low current power to the Hall effect sensors. The thick gauge wires are for the stator windings, and the thin gauge wires are for the Hall effect sensors. Let's go over what these specs mean when you go to purchase a brushless DC motor. The no-load speed is significantly higher than the rated speed, but that's not very relevant. Nobody buys a motor to run it under no load. The rated speed relates to how fast the motor will run when operating at the rated torque, shown in millinewton meters. What's interesting here is that the manufacturer offers the motor in two models, one that operates at 12 volts and the other that operates at 24 volts. The ratio of these voltages does not correspond to the ratio of the motor's speeds at virtually the same rated torque. Having the voltage from 24 to 12 volts slows the motor down not by a factor of 2, but by a factor of 2.55. Recall that back EMF is equal to angular velocity times the back EMF constant K sub E, and that the back EMF is subtracted from the input voltage to obtain the net voltage powering the motor. I never said, however, that the back EMF constant's the same number for all motors. In reality, it varies based on the exact dimension, material, and gauge of the motor windings. which is obviously different for these two motor models. The torque constant is the torque produced for every amp of current drawn by the motor. Since torque varies linearly with current, you can use it to extrapolate the current or torque below the level shown for rated torque and current. But here's an oddity for you to consider. If you multiply the torque constant for this motor by the current at rated speed, you get about 10% above the rated torque. Not exactly the rated torque. This was true for the other brushless DC motors that I checked online. This implies that torque versus current curve, while linear, does not go through the 0,0 point. Rather, the zero torque crossing for this motor is roughly 0.1 amps, meaning that you need to put a small amount of current into the windings to overcome mechanical friction before you can get the motor to rotate at all. Continuous stall torque is the maximum torque that the motor can deliver for a short time. It is left blank because it is not available at all speed ranges of the motor. The continuous power is the mechanical power that the motor provides to turn a load, not the electrical input power. To obtain the continuous power, you multiply the efficiency at the duty point times the rated current times the rated voltage. For example, the continuous power for the 24-volt model is shown as 20 watts, which is 75% times 1.1 amps times 24 volts. In fact, you get 19.8 watts, but the manufacturer chose to round up to 20 watts, the nearest integer. The rotor inertia is the mechanical moment of inertia for the rotating parts, shown in gram-centimeters squared. It is equal to the torque of the motor under no load condition divided by the angular acceleration of the armature. This motor has a somewhat limited temperature range, operating between 20 degrees C and 45 degrees C. The maximum temperature rise is 75 degrees K, which presumably occurs in the region around the coil windings, heating them up to a potential temperature of 120 degrees C. There is no forced cooling of this motor, which implies that exceeding a stator winding temperature of 120 degrees C could permanently damage the windings. Let's recap. Now you have a good understanding of how the stator phases drive a brushless DC motor. In the next video, we will explain how electronic commutation modulates the stator phases.